Hi all, welcome to the next video of compressible fluid flow video lecture series. In the last video, we had discussed in detail about Mach number, which is a non-dimensional number used to classify the compressible fluid flow into incompressible flow, subsonic flow, sonic flow and supersonic flow. Now we are interested in a phenomenon called sonic boom, which is closely associated with supersonic flows. Now let us see what is a sonic boom. A sonic boom is a sound associated with the pressure waves created whenever an object travels through the air faster than the speed of the sound. So this means whenever we are trying to increase the speed of the object or the flow and the speed is greater than the speed of the sound, the nature will try to oppose the effect of the increasing of the speed by producing a series of pressure waves or by producing a high pressure which is associated with the flow. Okay, so due to this high pressure wave, which will be a sudden increase in the pressure value, a cracking sound will be produced. Okay, a sudden explosive sound will be produced, and that sound is called sonic boom. Okay, so this is purely associated with supersonic flow. When we are trying to cross Mach number equal to 1, when we are trying to reach the supersonic state, this phenomenon will take place. So sonic boom generate enormous amount of sound energy sounding similar to an explosion or a thunderclap to the human ear. We all have heard an explosion, right? In films or in real life videos or something like that. Like an explosion, this sonic boom will also generate enormous amount of sound energy. Or we can relate this condition to a thunderclap. That is a sound of a lightning in a thunderstorm. It is similar to that. And also a general example is whiplash. Whiplash means chatavar. When we are using the whip to lash, it will create this sound, this sonic boom sound. And it is due to the velocity of the tip of the whip, which is traveling at a velocity which is greater than the velocity of the sound. So a sonic boom, a miniature form of the sonic boom will be created during a whiplash also. Now we will look into an example. An aircraft is traveling, it is flying from left to right as shown in this figure, and it is now having a Mach number equal to 2.92, which is definitely stating that the aircraft is traveling at a supersonic speed. And since it is traveling at supersonic speed, it will generate a Mach con as shown in this figure. Okay, now a man is standing on a hill, on a high ground, but he is still outside this Mach con. That means he is in the zone of silence. So he cannot hear the sound of this aircraft. Okay, so here the Mach angle is calculated to be 20 degree. Mach angle is a semi angle of the cone. That means it is only half of this total angle. Okay, so this is 20 degree Mach angle. So observer hears nothing until the wave fronts cross the Mach con. So whenever the man is inside this Mach con, he can hear the sound. Okay, we had discussed in detail about this condition in the last class. Now, when the aircraft passes through the air, so in the same condition, before the aircraft reaches this Mach number equal to 2.92, there was a condition when the aircraft reaching Mach number equal to 1. Okay, so that condition, we can say that the aircraft was trying to cross the sound barrier. Sound barrier is generally considered to be Mach number equal to 1. Okay, we can reach Mach number equal to 1 easily, not easily. We have to use certain resources and machineries, equipments, etc. Somehow we can reach Mach 1, but overtaking or surpassing Mach number equal to 1 is not an easy task. It will be very expensive and very complex process to cross this Mach number 1 condition in order to reach the supersonic state. Okay, so obviously the nature will try to oppose the effect we produce to reach the supersonic state. That means we are trying to violate the nature by crossing this Mach number 1 condition. That's why this condition is known as sound barrier. Okay, so if you are crossing the sound barrier, the nature will try to oppose by increasing the pressure of the flow. Nature will try to create a back pressure. That back pressure will be produced by a series of pressure waves which will be produced by the aircraft or the flow when it reaches the Mach number equal to 1, and this series of pressure waves will merge into a single shock wave which will be having very high value of pressure. Okay, so we can say that suddenly the pressure value will be increasing at Mach number equal to 1. Okay, we have a pressure value when, and after reaching the Mach number equal to 1, that pressure value will be suddenly increasing to a very high or a very large value, a very massive value. So that sudden increase in pressure will be very difficult to cross, and that process is called the crossing of the sound barrier. Okay, and due to this sudden increase in pressure, this sound energy, there will be an increase, there will be massive increase in sound energy, and due to that liberation of the sound energy, we will hear a cracking sound, just like a thunderclap or an explosion, just like we have discussed, and that is due to this high value, sudden change in pressure value. Okay, so that is closely associated with the supersonic condition when we are trying to reach the supersonic condition, and this shock wave forms a Mach cone. So when this sonic boom happens at a Mach number equal to 1, and after that only the Mach cone will be developed. Okay, so after the sonic boom, the shock wave forms a Mach cone and a vapor cone also. Vapor cone will be visible if sonic boom is audible at Mach number equal to 1, audible for only a few seconds, and after that Mach cone will be developed at supersonic condition, and as a result of the Mach cone there will be a vapor cone also, which will be visible at the surface of the aircraft. Okay, now sonic boom, this is an example for the vapor cone. Okay, this aircraft has just crossed the Mach equal to 1 condition. That means it has just crossed the sound barrier. That's why a sonic boom is here. I will show you a demonstration of a sonic boom. You can hear this sound. Okay, what you have just heard is sonic booms in the case of two different aircrafts. Okay, the sonic boom was heard for a brief moment or for a few seconds. So after a few seconds, we cannot hear the sound when the supersonic flow is achieved. Okay, so the sonic boom is experienced when there is a sudden change in pressure. And how this vapor cone is produced? The visible vapor cone, it is just like a cloud formation at the vicinity of the aircraft surface. And how it is formed? Just remember that sonic boom is will be developed at Mach number equal to 1 for a brief moment or a few seconds. After that it will go. We cannot hear sonic boom for a certain time. It cannot sustain longer. So after that vapor cone will be formed. This is closely associated with the Mach cone formation. Okay, so here a vapor cone, which is also known as shock collar or shock egg. It is a visible cloud of condensed water formed when the aircraft moves at high speed through the moist air. Okay, so there are certain conditions for this vapor cone to be formed. The conditions include the atmosphere should be moist. It should be having moist air, and also a condensation shall take place. This cloud formation, this visible cloud formation, is due to the condensation of the air which is close to the aircraft surface. And how this condensation occurs? Let us see. There is a rise in pressure at the nose, decreasing steadily to the negative value to the tail. Okay, so there is a positive value, high pressure at the tip of the aircraft, and decreasing to the tail of the aircraft, and at the tail it will be negative pressure. So the pressure value will be negative at the tail or at the back side of the aircraft. So what happens when this air pressure decreases? So when the localized air pressure around the object drops, which is at the tip, which is at the tail of the aircraft, so does the air temperature. When the pressure decreases, the temperature value of the air also decreases at the tail part of the aircraft. And since this temperature value drops below the saturation temperature, a cloud forms. Okay, we all know about dew point temperature, right? Whenever the temperature lowers or reaches the value of the dew point temperature, there will be condensation of air. Okay, due to this condensation, the drop air and the water content in the air will be condensed to droplets of water. And if you're considering this condition in the case of this aircraft, when the temperature drops below the saturation temperature or the dew point temperature, a cloud forms due to the condensation of the moist air or the condensation of the water content in the moist air. Okay, so in the case of the aircraft, this cloud is caused when the air pressure, density and the temperature, all these parameters fall below the dew point temperature. Now, for the easy comprehension, I have included a video, an animation of Iron Man flying at supersonic speed. Okay, so in the initial condition, he was traveling at subsonic speed. Now he has attained Mach number equal to 1 sonic condition, and after that he had crossed the sound barrier, and we can clearly see a cloud formation is taking place for a brief moment. Okay, that is example for our vapor cone. Now this is all about sonic boom and the vapor cone associated with the supersonic flow. Let us see some more examples for this vapor cone. So in the case of the propulsion, rocket propulsion also, we can see the formation of vapor cone. So this is a supersonic rocket propulsion. Its name is Ares 1X. It is a NASA program, and actually this rocket has a maximum speed of Mach number equal to 4.5. That is the maximum speed of this rocket. Okay, so obviously it has to be propelled with a velocity greater than the sound velocity, and there is a formation of vapor cone which can be seen in this diagram, in this photograph. And all the other three photographs are associated with supersonic fighter jets. The first one is a case of FA-18A at transonic speed. It is a supersonic fighter aircraft, and we can see the cloud formation of this aircraft at transonic speed. Transonic speed means the speed Mach number is between 0.8 and 1.2. If the Mach number is between 0.8 and 1.2, we can consider that region as transonic region. Okay. And the third one, we can see a complex formation of condensed air, or a complexity. We can see the complexities in the vapor cone. Okay, it is a case of an F-A-18C, which is also at transonic speed. Now the last photograph shows F-35 Lightning aircraft. It is a fighter jet which can also travel at supersonic speeds. We can see a double cone. Okay, in certain conditions, which is also based on the shape of the aircraft also. Okay, in certain cases, shape of the aircraft will cause a double cone. Due to certain shape of the aircraft, double cone formation can be visible. Okay, so these are examples for different types of vapor cone in the case of different types of aircrafts. Now we are going to another important derivation of energy equation. Okay, so for that condition, we are considering an example of open flow. Here the flow is open flow. We can see a control volume here, and the control volume and the control surface are shown in this figure. So here the initial conditions of the flow was C1. C1 was the initial velocity, P1, V1 and H1. H1 is the enthalpy. And after the process or after the flow is taking place, we have the final conditions C2, ρ2, V2, H2, etc. Okay, and heat transfer also is shown here, Q. And there is a shaft work associated with this flow, which is shown by WS. Okay, So this is an open system, since matter is coming to the control volume and matter is going out of the control volume. So this is an open system, not a closed system. In the case of solid closed system, mass cannot be coming through to the system, and mass cannot be going out from the system. Okay. So we are also considering a altitude in two conditions. In the case of initial condition also, we will consider the altitude as Z1, and in the final state the altitude as Z2. Okay, so there is a datum where the altitude value, Z value, is equal to 0. This is a datum. Now, as per the first law of thermodynamics, we all know that as per the first law of thermodynamics, heat transfer Q is equal to W, that is the work, plus the change in energy, which is E2 minus E1, change in energy between the two states, final state and initial state, difference of energies between final state and initial state. And this term E, energy term E, may include different types of energies like gravitational potential energy, kinetic energy, internal energy, strain energy, and magnetic energy. Okay, so it is actually a total value of energy, and different energy components are listed here. But certain types of energies like strain energy and magnetic energy, they are very small in quantity and can be neglected when compared to the values of other quantities like gravitational potential energy, kinetic energy, and internal energy. So finally the equation will change like this. First we will write the energy equation. So we will consider the internal energy and gravitational potential energy, which is mgz. Internal energy is capital U, and kinetic energy as half mc square. Okay, instead of v, we will write the fluid velocity as c in this condition. So capital E is equal to U plus mgz plus half mc square. This is our total energy equation. And we have ignored the other forms of energy like strain energy and magnetic energy. Okay, and the differential form of this equation is dE, which is du plus mg dz and m into d of 1 by 2 c square. Okay, we are taking the differential of 1 by 2 c square, and this can otherwise be written like this: E2 minus E1 is equal to integral. We are applying limits here, integral 1 to 2 dE, and applying limits, integrating and applying limits to the internal energy also. So integral 1 to 2 du mg integral 1 to 2 dz plus half m. We have taken the half outside, and we are integrating c square with respect to the limits 1 and 2. So half m integral 1 to 2 dc square. Okay, we haven't differentiated c square. Okay, we are taking the c square inside the differential. Okay, so we are not differentiating c square into 2c or something like that. Okay, that has to be noted. Now this is rearranged like this. After applying limits, internal energy can be written like this: U2 minus U1 plus mg into altitudes after applying limits, z2 minus z1, and square of the velocity c2 square minus c1 square after applying the limits. And for a more general form of the energy equation, we are now substituting this whole equation to our first law of thermodynamics. Therefore Q is equal to W plus, for E2 minus E1 we have written the whole equation we have derived here. Okay. Now in terms of specific values, we can change this equation in specific terms by dividing mass with all the components of the equation. So capital Q by mass will be small q, specific heat transfer. Similarly, work will be small w plus U2 minus U1 plus G into Z2 minus Z1 plus half C2 square minus C1 square. Mass has been cancelled here and here. In the case of gravitational potential energy and also in the case of kinetic energy, mass term is cancelled. So this can be considered to be a more general form of the energy equation. Now, what all changes we can consider in this equation, and finally we can use this equation for our certain equipments which will be used for compressible flow conditions. Okay, so there will be certain changes to this equation. This is not the final form which we can use for the stated equipments like nozzles and diffusers. Those are the equipments we are mentioning here. We cannot use this equation directly in the case of a nozzle or diffuser. We have to change certain components, or we have to apply certain conditions to these equations before we will going into those equipments case. Now, energy equation for non-flow process. In the case of non-flow process, what is a non-flow process? Processes in closed systems like expansion and compression of gases in a cylinder with a piston. Those type of processes can be considered as non-flow processes. So the potential energy and kinetic energy terms in the case of such processes are negligible. So in the previous equation we can neglect potential energy and kinetic energy. And another change associated with a non-flow process. Here the work term will be known as shaft work. For a non-flow process, the work term will be shaft work. So our W will be, in this case it will be written like Ws, W suffix S. So our first law of thermodynamics equation, energy equation, is written like this: Q is equal to Ws, which is the shaft work, plus U2 minus U1. Only internal energy is considered. Potential energy and kinetic energy are neglected. Now the assumption of perfect gas gives, before that we have differentiated this equation, therefore dq is equal to dws plus du. So assuming perfect gas, we can write our shaft work as pdv. P into dv is our shaft work, and du, differential of our internal energy, can be written like this: ncv dt, m into cv dt, where cv is the specific heated constant volume. Now integrating this equation will give q. On the left hand side we will get q is equal to integral 1 to 2, our limits are from 1 to 2, integral pdv 1 to 2 plus mcv t2 minus t1. This is after applying limits after the integration process. So t2 minus t1. Now we haven't yet integrated this term. That is because that term will depend upon the type of the process. The process can be isobaric process, isothermal process, etc. So this term will depend upon the type of the process. So we will not integrate this term until the type of the process is stated. Okay. So this is a general equation for heat transfer in the case of a non-flow process. Now in the case of flow process, now what are the examples for flow processes? Processes in open systems like expansion of steam and gases in turbines, in the case of turbines, or in the case of turbo compressors, compression of air and gases in turbo compressors. These types of processes are known as flow processes. Okay, so it will be open system, just like we have discussed in the starting of this topic, energy equation. We have considered an example of open system. So that is an example for flow process. Okay. In such processes, the work term W includes flow work also. So here the work term includes flow work. In addition to the already existing work term, we will be having a flow work term also in this case. So our work term will be written like this: shaft work, which is already existing in the equation, plus P2 V2 minus P1 V1. That is considered to be flow work term. Okay. Flow work term can be written like this: P2 V2 minus P1 V1. So this is a change in our work component. Okay. In the case of non-flow process, W was equal to just Ws, shaft work. But in the case of flow process, we need to additionally include P2 V2 minus P1 V1, which is the flow work. Therefore changing the equation. So applying to the first law of thermodynamics equation, Q is equal to Ws P2 V2 minus P1 V1. So this whole term indicates our work, plus internal energy U2 minus U1, plus gravitational potential energy mg Z2 minus Z1, plus half m C2 square minus C1 square. This is after differentiating and integrating and applying limits, this equation. That's why U2 minus U1, C2 Z2 minus Z1 and C2 square minus C1 square. Now rearranging this equation. So grouping these terms together, U internal energy term and the product of pressure and volume terms together, we can change the equation like this. We all know that U plus PV, where U is the internal energy and the product of pressure and volume, U plus PV is equal to our enthalpy. It is enthalpy. So this equation can further be simplified by using the enthalpy terms. Okay. Therefore, Q is equal to Ws, and this H2, U2 plus P2 V2 can be written as H2. Similarly, U1 plus P1 V1 can be written as H1. Okay. Plus mg Z2 minus Z1 plus half m C2 square minus C1 square. Now, again we are changing the equation by grouping the terms with suffix 1 to the left hand side and terms with suffix 2 to the right hand side. We can write the equation like this. And in terms of specific values, we can divide all the terms with mass so that the equation will be changed like this. Okay. The above equations, these two equations can be treated as steady flow energy equations. We have studied about steady flow energy equations in thermodynamics, right? So these equations are same as the steady flow energy equations which we have derived or studied in our subject thermodynamics. Okay. Generally in flow problems, now in the case of vapors and gases, we don't need to consider the altitude, since gases and vapors generally doesn't have altitude unless they are flowing through a duct or pipe or something like that. So generally in the flow problems of gases and vapors, we can neglect the magnitude of terms containing our altitude, or the difference in altitude can be taken as a negligible value. Therefore, G into Z2 minus Z1 term is negligible and can be cancelled. Therefore, the equation is further reduced to a form like this: H1 plus half C1 square plus Q plus H2 plus half C2 square plus Ws. All terms are in specific form. Okay. This is also steady flow energy equations in the case of gases and vapors. This is not the final equation which we can further use for the case of nozzles and diffusers. We need to further change into another presentable format of this equation by considering certain conditions. Now finally, adiabatic energy equation. This can be considered as the final form of the equation, final form of energy equation which can be used in the case of our flow devices like nozzles and diffusers. So what all changes we have to consider here? In some engineering problems, heat transfer Q during the process is negligibly small. So we can cancel the Q component from the previous equation. So some examples are shown here. Expansion of the gases and vapors in turbines are examples. For such processes, so in the case of turbines, we all know that in the case of turbo compressors and turbines, etc., there won't be any heat transfer. Okay, heat transfer will be equal to 0. Okay, they will be thermally insulated. So the Q term will be equal to 0 when we are considering these situations. For such processes, the equation reduces to H plus GZ1 plus half C1 square plus H2 plus GZ2 plus half C2 square plus Ws. The Q term has been cancelled. Now, reducing to this form. We can reduce to this form by considering the case of gases and vapors. In the case of gases and vapors, we can neglect the difference between the altitude. So G into Z1 minus Z2 can be cancelled. So this is finally reduced to this form. And one more reduction is associated with adiabatic energy transformation. So in the previous adiabatic energy equation, which are valid for the processes involving energy transfer on account of shaft work. So in all these mentioned examples, in the case of turbines, turbo compressors, etc., there will be a term called shaft work, because a shaft work will be associated with all these situations. Okay, Now we are finally coming to our flow devices like nozzles and diffusers. Since nozzles and diffusers, for example, I will draw a diagram here. Okay, in the case of nozzle is a flow device like this. Okay, its area will be gradually decreasing, and the diffuser will be a flow device like this. Its area will be gradually increasing. Okay, so the flow will be taking place from this side to this side. Here also the flow will be taking place from this side to this side. So this is a nozzle, this is a diffuser. And in the case of nozzle, our pressure value will decrease, and in the case of diffuser, our pressure value will increase. Okay, so these flow devices are used for compressible flow processes. Okay, different in the case of aircraft, in the case of jet propulsion, rocket propulsion, etc. Nozzles and diffusers will be used throughout. So we need to convert our existing adiabatic energy equation, and those equations will be have to be suitable for this two cases, in the case of nozzles and diffusers. Okay. Now back to our adiabatic energy equation. So in this case of nozzles and diffusers, expansion of gases in the case of nozzles and compression of gases in the case of diffusers. In both these cases, shaft work will be absent. Okay, if you remember correctly, the diagrams which I have drawn, I haven't even drawn a shaft. Okay, the shaft was absent in those two cases. In the case of nozzle and also in the case of diffuser, there won't be any shaft. So shaft work will be completely absent in the case of nozzles and diffusers. So in those conditions, the equation can be further modified into h1 plus gz1 plus half c1 square is equal to h2 plus gz2 plus half c2 square. And if you are considering the case of gases or vapors, we can change the we can neglect the elevation terms. Therefore g into z1 minus z2 can be neglected. And finally, the most important equation called adiabatic energy equation after adiabatic energy transformation has been obtained. This is a very important equation. h1 plus half c1 square is equal to h2 plus half c2 square. Or generally we can write like this: h plus half c square, I will write here, h plus half c2 square, sorry, h plus half c square is equal to constant. Okay, this equation is considered to be a general form of the adiabatic energy equation, which can be directly used for analyzing the flow, compressible flow process in nozzles and diffusers, which will be further discussed in the coming classes. Okay. So that is the end of the today's class. We have discussed about a sonic boom and vapor cone formation, and after that we have introduced the concept of energy equation, which is closely related to first law of thermodynamics, and we have changed our energy equation on the basis of the flow equipments we are considering in our study, compressible fluid flow analysis, and we have finally reached to a general form of the energy equation, which can be directly used in the case of analyzing our flow equipments like nozzles and diffusers. So that equation is h1 plus half c1 square is equal to h2 plus half c2 square, or generally h plus half c square is equal to constant value. This is generally considered to be adiabatic energy equation. Okay, so see you in the next video. Thank you.